This second part of quality control of concrete on site will examine the test methods for air content and unit weight, plus the procedures for making cylinders and beams for compressive and flexural strength tests. To begin, air content test methods. The results of air content tests indicate the freeze-thaw durability of concrete. Air-entrained concrete with the specified air content performs much better than non-air-entrained concrete in freezing and thawing conditions. On the job, concrete can be rejected if its air content is not within the allowed range. The most popular method for measuring air content is the pressure method. Two types of pressure meters are available and are widely used. They are referred to as Type A and Type B, and are covered in AASHTO T152. With Type A air meters, the equipment needed includes a calibrated Type A meter, a tamping rod, just like the one used in the slump test, an internal vibrator, a rubber or rawhide mallet, a scoop, a strike-off bar, and a supply of fresh water. The meter consists of a measuring bowl having a capacity of at least 0.2 cubic foot, and a cover assembly that includes a standpipe, a pressure gauge, and an air pump. The cover assembly also contains a number of valves and petcocks. The bowl and cover must clamp together to form a pressure-tight seal. As with the slump test, all the equipment should be clean and in good condition. It should be assembled near the concrete sample. The test is begun by filling the measuring bowl with concrete in either 2 or 3 equal layers and consolidating each one. The number of layers depends on whether the consolidating is done by rodding or vibrating. And the method of consolidation depends on the result of the slump test just performed. If the slump is less than an inch, vibrating is required. If it's more than 3 inches, use the tamping rod. And if it's between 1 and 3 inches, either method can be used. When the tamping rod is used, the bowl is filled in 3 equal layers. Each layer is rodded 25 times, and the strokes are distributed evenly over the cross-section. The bottom layer should be rodded throughout its depth, but without forcibly striking the bottom of the bowl. After each layer is rodded, the sides of the bowl should be tapped sharply with the rubber mallet 10 to 15 times around the bowl's circumference. This will close any voids left in the concrete by the tamping rod and release any large entrapped air bubbles. In rodding the second and final layers, only enough force should be used to penetrate the surface of the previous layer about 1 inch. Then, the final layer of concrete is added without excessively overfilling the bowl. When the vibrator is used, the bowl should be filled in 2 layers of approximately equal volume. After the first layer is added, the vibrator is inserted 3 times at points evenly distributed over the cross-section. The vibrator must not touch or rest on the bottom or sides of the bowl, and the concrete should not be over-vibrated. Such practices segregate the aggregate and lose some of the intentionally entrained air. The final layer is added without excessively overfilling the bowl. Then, it's vibrated the same way the first layer was vibrated. Usually, the surface has been vibrated enough when it's relatively smooth and looks glazed. The surface should then be struck off by sliding the strike-off bar across the top flange or rim of the measuring bowl. Then, the contact surfaces are wiped clean and the cover assembly is clamped firmly to the bowl. The lower petcock is closed. The upper petcock and funnel valve are opened. And water is added until it rises to about the halfway mark in the standpipe. The meter should be gently rotated and tapped with the mallet to remove any entrapped air that may remain. Next, water should be poured through the funnel valve until it stands at a level slightly above the arrow mark on the graduated scale. The funnel valve is then closed and the level is adjusted to the arrow mark by drawing off just enough water through the lower petcock. Next, the top petcock is closed and pressure is applied with the air pump until the gauge reaches the exact air pressure required. The required pressure is known from the calibration procedure. Now, the resulting water level is read, the bottom of the meniscus on the graduated scale. This value is the gross percentage of air entrained in the concrete, or H sub 1. Then the pressure is released, and the water level on the graduated scale is read. This value is the lag, or H sub 2. The air content of the concrete is the gross percentage, H sub 1, minus the lag, H sub 2, minus an aggregate correction factor, G. Determination of the aggregate correction factor using both meters is covered in T152. The Type B test requires a calibrated Type B meter as well as the same equipment needed for the Type A test. The first step is to fill the bowl with concrete, consolidate it, and strike it off, the same as for Type A. Then the flange is wiped clean and the cover is clamped on with both petcocks open. Water is then injected through one petcock until it comes out the other petcock. With both petcocks open and the air bleeder valve closed, air is pumped into the air chamber until the gauge hand is on the initial pressure line. To stabilize the gauge hand at initial pressure, air is pumped in or bled off as necessary, and the gauge is tapped lightly. Next, both petcocks are closed and the thumb lever is pressed down. This releases the air into the bowl. The sides of the bowl are tapped sharply with the mallet, and the gauge is tapped gently with the fingers until the dial hand stabilizes. This is the gross air content percent. From it, the aggregate correction factor is subtracted. The result is the net air content percentage of the concrete. Now it's time for the unit weight measurement of fresh concrete. The unit weight, or density, is determined simply by weighing a known volume of the concrete according to AASHTO T121. The same equipment used for air content testing is needed, as well as a measuring container, or measure, a balance or scale, and a strike-off plate. The balance or scale must be accurate to within 0.3% of the test load. The measure must be a watertight cylindrical container whose capacity depends on the size of aggregate used in the concrete. For 1-inch maximum size aggregate, a measure with a minimum capacity of 0.2 cubic foot should be used. If the aggregate has a maximum size of 1.5 inches, the measure's minimum capacity should be 0.4 cubic foot. And for 2-inch maximum size aggregate, the minimum capacity should be 0.5 cubic foot. Since the air content meter's bowl has a capacity of 0.2 cubic foot, it can be used as the measure when the concrete contains 1-inch maximum size aggregate, as is becoming more common in pavements and bridges. The first thing to do is place the empty bowl and strike-off plate on the scale or balance and record the weight. The bowl is then filled in 3 equal layers of concrete, with each layer properly consolidated. Consolidation requirements are the same as for the air content test. If the slump is less than 1 inch, you vibrate. If it's more than 3 inches, you rod. And if it's in between, you have the option. The concrete surface is struck off and finished using the strike-off plate. The bowl must be exactly level full. Then all excess concrete is cleaned off the outside of the bowl, and the filled bowl and strike-off plate are placed on the scale or balance. The net weight of the concrete is determined by subtracting the empty weight of the bowl from its filled weight. To calculate the unit weight, the net weight of the concrete is divided by the calibrated volume of the bowl. The last topic is the making of concrete cylinders and beams on site for subsequent compressive and flexural strength tests. Other than the molds, all needed equipment is available from the other tests we've covered. The sizes of molds are based on the concrete used and on specific project requirements. To begin, the proper molds must be on hand and clean. The concrete is placed in the mold using the scoop or trowel. Then, the tamping rod is used to distribute the concrete evenly across the full area of the mold before starting consolidation. The number of layers required to fill the mold depends on the mold size or depth. Table 1 of AASHTO T23 details the specific mold requirements. For common molds, such as cylinders with depths up to 12 inches, the concrete is placed in 3 equal layers for rodding and 2 equal layers for vibrating. For beams with depths between 6 and 8 inches, the concrete is placed in 2 equal layers for rodding and just 1 layer for vibrating. Selection of the consolidation procedure depends on the slump, just as it did for the air content and unit weight tests. Less than 1 inch, vibrate. More than 3, rod. In between, optional. When rodding is used, the number of strokes is usually 25 for the most common molds. Table 2 of AASHTO T23 gives the requirements for other molds. After each layer is consolidated, the outsides of the mold are tapped lightly 10 to 15 times to close any holes left by the rod or vibrator. When beams are made, the tapping of the mold should be followed by spading the concrete along the sides and ends with a trowel or other suitable tool. To finish the cylinders or beams, a small excess of concrete is added to the surface, but not more than a 1/4 inch. Then the surface is struck off. Normally, a wood or magnesium float is used to finish the surface, but a steel trowel is used if specified. Immediately after they're finished, the mold should be covered to prevent evaporation. Polyethylene sheeting is usually used for this purpose. Alternatively, wet burlap may be used, covered by plastic. In this program, and in Part 1, you've seen the on-site procedures for sampling fresh concrete, testing it for temperature, slump, air content, and unit weight, and making cylinders and beams for compressive and flexural strength tests. In Parts 3 and 4, you'll see new concrete testing and monitoring procedures developed by Sharp and others. The careful following of proper sampling and testing methods greatly enhances the quality control of concrete on site.